this advantage. Please, Klaus, the floor is yours.
Yes. Thanks, Mathieu. Thanks, everybody, for inviting me and giving the chance to talk about a topic that is maybe not very, let's say, in your main research. I will talk today about spins as probes. So I work in a research center, the Helmholtz Center, where we are developing all kinds of technologies for solar application, which is mainly solar cells. We are setting up new chemical reactions for catalysis, electrolysis, and also look at loss mechanisms in batteries. And the second part, what we do is quantum information science. And actually, I work in both fields, energy conversion and quantum information science. And my department is dealing with the question, how do spins, on the one hand, are involved in energy conversion and quantum information science, and what can we learn from spins in the material? And today, I would like to talk only about a very single topic, and that single topic is going to be loss mechanisms in solar cells. So I will talk about this topic only because I just want to give you an example on how you can learn how an electron or a nuclear spin can be used as an observer. You read out that information. I will read it out electrically. And then with calculations, you learn how a solar cell actually is working. That is the idea of this talk. And at some point, it might get a bit too detailed maybe, but then just don't mind. The main idea is that you understand how you can manipulate a spin. So if you look at spins generally in materials, we have radicals. Radicals play quite an important role in electricity production. It plays a role in sensor technology, in computing, energy storage. Diseases are induced by radicals. Medication, environmental pollution, food quality, it all deals with radicals. And these radicals, they have, in many cases, magnetic properties. And it is about these magnetic properties, namely the net magnetic moment of, for instance, a free radical, which could be a broken bond or an excited state, that is the electron spin. And such radicals, they can control chemical reactions, like in catalysis. I will talk about recombination in solar cells, so loss mechanisms on where charges simply disappear. And these charges, they disappear, for instance, in semiconductors around defects, and they are often associated with electron spins. And these spins then control the efficiency of a solar cell, and I will show you how a bit later. Of course, in biological processes, these radicals are extremely important. We know that if you get an inflammation, this is induced by radicals. Cell aging is radicals. Hypertension goes through radicals. So if you understand how and what this radical is that is doing something, and you probe its environment, you learn something about the structure-function relationship of such radicals. And that is actually what my work is about. These radicals are entities that have a magnetic moment. That magnetic moment then in the sample sums up to all the individual radicals that we have, 10 to the 10 maybe per cubic centimeter or even more. And we are then monitoring that total magnetization of the sample to learn something about the structure-function relationship, seeing what these radicals do in the sample. And to do that, we have to lift the degeneracy of the spin state, and we do that by putting it into a magnetic field, then spin up, spin down, have different energy splittings, and you can do very nice spectroscopy from which you then learn something about the environment. That's what I will talk about today. And the main feature of such a spin system that is doing something in a system is basically picking such a signal up, and then looking on how that signal is basically responding. It seems that my animation is not working. Let me see whether I can repeat that. No, unfortunately, this one is not working, but that's how it goes. Never mind. I will show that later again. Okay, so radicals or spins in solar cells, I will now start to discuss a bit. Now, first, before we do that, we have to understand what is actually a solar cell. A solar cell is converting light energy into electrical energy. And that means we need some device that is absorbing the light, or it's absorbing the photons, and is then converting those photons into charges, electrons and holes. And a typical material is silicon. And what the light is doing that is entering that silicon solar cell, it is being absorbed by the silicon. So these arrows, let's say, are the waves that come into the material. Now, in silicon, we are generating only charges once that fundamental threshold energy is beaten by that of the light. So we have to be higher in energy than the fundamental threshold. In silicon, it's the band gap, which is about 1.1 electron volt at room temperature. The free charges that you then generate inside that material, they basically, let's look at electrons and holes. Let's assume this is an entity that has been generated. This electron will wander around the sample and just do whatever it wants. The same is true for the holes. I will use the blue color for the holes. The hole will do the same thing. It will just basically wander around in the sample. If they meet again, they recombine. How do you now get a current? You can only get a current if you have what we call selective contacts. That is a contact that, on the one hand side, I've drawn it in blue. It's a contact that only lets holes through, and on the other side, a contact that only lets electrons. So let's assume we have such contacts. What it means is that the electron is wandering around. Once it hits this side, so the right side, it cannot get out, but once it makes it to the left side, it can go through that contact and can be collected. The hole, the positive charge, is doing the same thing, but goes out at the blue contact. And by that, you get a direct current. And that is the current that we use to drive devices or use it in any other means that we want. The challenge is now that the electrons and holes that you generate survive long enough in order to reach the contact. And it means the mobility or the lifetime, the diffusion length has to be high enough so that the average length that they can travel is so small, so large that they get to the contact. And of course, that selectivity of the contact then determines how well that solar cell is working. So this basically is exactly how a solar cell works, and that's actually all that you need to know for the remainder of the talk. If you go to a bit more physical picture, you would show it like this. So we have a silicon material. I will give you the borders of the silicon material. This is the silicon material in between those dashed lines. This axis is an energy axis. And this, of course, this energy is the band gap that we have right here. That's the band gap. So once the energy of the photon is higher than that band gap, we can now excite an electron-hole pair across that band gap. And now, how does the selectivity work? Well, you can see the electron now that has been generated, or many of those electrons that have been generated. And you can see if that electron wanders in this picture to the right, it will hit on the right-hand side a barrier, because the selective contact is a contact that has a barrier with respect to the electrons going out. The electrons cannot make it through that barrier. They will be repelled and can only go out on the left-hand side because there the energetics allowed. The same is true for the holes. However, here the barrier is on the left-hand side and they can only go out on the right-hand side. The physical picture is then you have to describe the chemical energies inside the system. You do that by calculating the quasi-Fermi levels. Let's not go into those details. But in a typical silicon solar cell, a very modern typical solar cell, so the Reckitt efficiency of those is almost 27%. These selective contacts are extremely thin, only 8 nanometers. So they are very thin compared to 150 nanometers of the thickness of the absorber material that you need to harvest all the photons that have an energy above the band gap. In principle, silicon can do 29.3% as the efficiency, the theoretical efficiency. And so with the 27, we're already very close by, showing how perfect this device is. And for such a selective contact, there are a couple of rules. Rule number one is, of course, it has to be transparent so that the photons, let's say the photons come in from that side, that they are not absorbed in there. You don't want to lose those. And number two, the conductivity of the selective contact has to be high for electrons for the electron selective contact, and high for holes for the hole selective contact. So they need large band gaps and at the same time a very high conductivity. That's what makes a perfect selective contact. Okay, and when you now look at these selective contacts, you will immediately notice that we now have not a homojunction like old solar cells, p-n junction solar cells. They were all homojunction solar cells, meaning the selective contacts were also silicon, crystalline silicon. This is no longer the case with the record solar cells, and all the future solar cells will not have homojunctions anymore. They have this exact selective contact, and that means where the two materials meet, the selective contact material and the silicon material, there we get a so-called heterointerface. That means we might have different bonding configurations, and there you create an interface. And at that interface, of course, things can go wrong. And that's what this talk is going to be about. What can go wrong at that interface? Now, the best selective contact that we can make for a solar cell is the selective contact between crystalline silicon, so ordered materials, and disordered silicon, which is called amorphous silicon. It is within an atomic layer, we get a transition from crystalline phase, which ends here, into an amorphous phase. That's quite an art to do that, but it's possible. So within one atomic layer, we get an abrupt change into complete disorder. Now at that interface, now defects can be created. We will talk a bit more about those defects. And these defects are mainly either bonds that are not connected to the amorphous silicon. So basically, I show the enlargement here. This, for instance, would be a silicon attached to an amorphous silicon. And you can see here, nothing is attached. That is a broken bond. And that means it contains one electron, and then it's a radical. And these radicals, they can harvest electrons. They can capture electrons, and that's why it's a loss mechanism. These defects have magnetic properties. These are typically in the middle of the band gap. So if they are here, they have positions right here, and an electron and a hole can basically jump into these defects and disappear. And that is a loss mechanism. And that, of course, you want to minimize in a solar cell. Okay, this amorphous silicon is quite an interesting material. I've been working in this field now, I would say, over 30 years. And that's also where I met Antonin many years ago. And the main feature of this amorphous silicon is that we have basically a local order. The order around any silicon atom within that amorphous silicon still has the near order of silicon, mainly a silicon atom, which I'm highlighting here, is still bonded or mainly bonded to 4 other silicon atoms, but the nearest and second nearest and third nearest neighbors, you get complete disorder. This leads to the fact that that band gap of silicon of 1.1 opens up, and what happens is, this is the density of states of crystalline silicon. We have no states in between. This is the band gap. And in amorphous silicon, the band gap opens up. And in between, we now get a lot of states that are localized states that can interact with our charges. So those are actually defects. And these states are close to the extended states, to the conduction and to the valence band, and are called tail states. They're shown here in magenta. Now, due to that, these states are stress bonds. So there is a lot of stress between the bonds, and that's where they form these localized states. But sometimes these bonds rupture, they form defect states, and these defects in such a material are so many that this material will definitely not work as a solar cell material. So you have to passivate those defects, get rid of their activity, of their radical nature, and you do that by using hydrogen. And this is, I'm marking that now in blue. These are hydrogen atoms that you put into the material. It attaches to the bonds and passivates those bonds and getting them out of the band gap. And so they are no longer active. You can do that quite well. Unfortunately, not in a perfect situation. So that material clearly has worse electronic properties as compared to crystalline silicon. But remember, that layer is extremely thin, only a few nanometers. So we don't care. We just have to get those electrons and holes through that layer. And once they are through that layer, they can be they are collected by for instance, a metal. Okay, so that's the basic idea of this amorphous silicon. And I will now show you what that does with respect to how charges behave in that material. Let's assume we have this perfect crystal here, and let's assume at that surface there is a single defect, a single ruptured bond. Let's assume there's no amorphous silicon on top. What is this now doing with respect to charge harvesting? Now, that forms a mid-gap state. That defect in the middle of the band gap, we create an electron hole pair, and that electron hole pair is then basically that electron can be captured at that defect. It charges the defect, and then a hole comes and then gets rid of it. If we now put amorphous silicon on top of this layer, the amorphous silicon on top is going to produce lots of these band-tail states, and these band-tail states now lead to the fact that these states can trap the charges. They make them very unmobile, and it makes the whole situation very, very complex. So we have a very complex interface where the mobility of the charges is rather poor. It's about 500 times less than in silicon, in crystalline silicon. And these states open up pathways for recombination at that interface. So basically a loss mechanism for those electrons and holes. But if you now look at this picture and you look at this snapshot, how many of these states are singly occupied? You can see this state has a single electron, so that will carry a spin. This state can carry a spin. That state can carry a spin. There is a spin. If we now excite an electron hole pair, this one will also carry a spin. If this goes out like that, this will also carry a spin. So there is zillions of spins inside that material. And from those spins, we will learn really a lot. Okay, now let's look at what these defects will do at such an interface. Now let's assume we have these defects, and they will produce then some solar cell current. And the solar cell current we can easily calculate. It's a p-n junction type solar cell. So we unfortunately the pen is also not working well. Okay, there you go. This is the solar cell current. It is an exponential function, and this blue thing is the dark current. That dark current is basically telling us how the diode is behaving. This is the dark current of the solar cell. It is exponential, and if you look at the IV curve being the current that we get out of the solar cell just by applying a voltage versus the voltage, we get that blue curve. So this is the dark current here. If we now shine light on the solar cell, due to the selectivity of the contact, we are now generating a photocurrent. That photocurrent is going in the opposite direction as the dark current. And that means for every photon that is being absorbed and the electrons being collected, it will produce a negative photocurrent. And that pulls down the dark current below the zero line, and we can then get the overall red curve, which is the IV curve of the solar cell. And it is so simple as I've explained. This current here, this is the short circuit current that tells you how many photons have been absorbed in generally. And we have the point where there is no current flowing, and that is the open circuit voltage. In between these 2 points, we have the point, and this is called the maximum power point, where we can withdraw the maximum power from the solar cell. That's where we want to run the solar cell. Now, a very important feature here is that always that open circuit voltage is always smaller than the band gap of the material, and that has to do with the fact that the potential between here and there can never be larger than the band gap. That is thermodynamics. Now, what happens if we have these localized states in the material? These localized states, they can do a very harmful thing. And what they can do is they can form states inside this amorphous silicon, and the holes, for instance, they can leak out by tunneling through these states like that. They tunnel through and produce a leaky tunneling current, or vice versa, electrons are being injected through that contact. What is that doing now with my dark current? Well, the dark current is now going to be much higher because I'm injecting additional electrons into the system. And that means this current J0, the prefactor, is becoming bigger. And that leads to the fact that at a given point, the dark current will increase. So if we look at a certain voltage, it increases from here to there. If we assume that the photocurrent is absolutely the same, we again pull down the IV curve by the photocurrent, and we get the dashed line. And you can now see in the dashed line, because of the leakiness, we have a reduced voltage. And that means we have reduced output pi of the solar cell. So that is why a leaky contact is going to reduce the voltage that we maximally can get out of this device. And so we have to minimize that leaky contact. Now, how do we know that we have such a leaky contact? We don't. There's many ways in how you get leaky contacts. This is one example that many people have thought about. And I will now show you an experiment how you can really measure that this is a leaky contact in the solar cell. And this is a very recent publication. So what I'm showing here is work that has just been published. What we have done is we've taken this solar cell, we have put it into an atomic force microscope where a cantilever is basically looking at the surface of that selective contact. And we are imaging the current through that solar cell with this AFM tip right here. We now shine light on the solar cell, generate electrons and holes, and with the cantilever, we pick up that local current. And just by scanning, we will then learn how the leakiness of that contact is working. And we're the first to do that. It's quite a tricky experiment. You have to do that under ultra-high vacuum conditions because you don't want any dirt being collected during the time that you do the experiment. And it's a room temperature experiment, and it gives you then results on the current. And I will directly now show you the results. On the left-hand side, we have the current image. On the right-hand side, we have the atomic force microscopy image, which is the force image of what the cantilever is actually seeing. And what we see is basically two things in the conduction picture. We see a negative current that is brown in this case. And in that brown background at a certain voltage, we see these white spots. And these white spots is a positive current. So we have basically a background decorated with hot spots where a positive current is flowing. And positive current is a dark current. Negative current is a photocurrent. So it seems that we have a separation of the two here. And then you can look at various spots. So for instance, you'd look at spot number 1 here. You go across that spot with your current measurement, you fit, and what you find is the spot size that we see there is roughly 1 nanometer. So these local shunts that we have a size of 1 nanometer. If you compare this now to AFM, this is the same position. We do the same scan with AFM. You can see that in AFM, we get a very different contrast as compared to the current. So obviously, this has nothing to do with the surface. These two images are not correlated. That's the bottom question. And this we have now analyzed to understand what are those states that are doing this local current. So that is, in a sense, nano spectroscopy. So we have, and we call them current patches because they form a positive current. Okay, the brownish area, that is the homogeneous area in the back. That is just a photocurrent. So somehow that photocurrent just leaks over independent on where we look. Now, what you can do is you can now check on this behavior as a function of the applied voltage. So if you go towards that open circuit voltage, you should see changes. If you go beyond, you should only see a positive current. And that's what is happening. We start at 0 bias. So this here is 0 bias. That's short circuit. And then you increase the voltage, and you can see from a very homogeneous background, now suddenly spots are appearing. And that means with increasing voltage, we get more and more of these hotspots in that measurement. And the length of this image is 100 nanometers. And they are these 1 nanometer sized spots that we see. And sometimes we also see that certain spots simply disappear. For instance, this spot here, that one here, is here almost disappearing, and here it is gone. So spots come and go with applied bias. And what we have then done is we have determined how many of these spots do we see as a function of the applied bias, do some calculations, and then convert that into energy, and then find out what is the density of states of these spots. And what we find is that it is an exponential density of states, and believe it or not, it matches exactly the density of states that we have for amorphous silicon for Hole states. So from this very simple experiment, it seems that we're somehow seeing band-tail states, but that is just due to the fact that they have the same number. This can be a coincidence. So what we actually need is a real proof that these are band-tail states. And I will give you that proof later. Okay, what we now can also do is we can now measure a local IV curve. Typically, an IV curve means you have a contact. That contact is integrating over a large area, let's say over centimeters in a solar cell. We now have a tip that is only basically a platinum tip that is collecting at a very local spot over only a few nanometers. So we get a nanoscopic IV curve. And for instance, we take our surface, we measure at that current patch here, and now we measure an IV curve. And you can see this is what the IV curve is showing. We have a constant current at low voltage. Then we go through that open circuit voltage, and then it becomes purely positive. So this point here is the open circuit voltage or the photovoltage of the solar cell, and that gives us a value of 0.5. The silicon band gap is right here. So that's a rather poor open circuit voltage. So it's not, seems not to be very good. Now we go to a different spot in our sample, and at a different spot, we can go, for instance, if we go to that spot here, we can see that the open circuit voltage is a bit higher, but the current here that we see here is the same. And we have done that now for over 1,000 different spots over the whole solar cell. So we measured up and down, left and right, everywhere. And if you do that, you find quite an amazing result. You sometimes find IV curves where the open circuit voltage here is larger than the band gap of silicon, which, as I said, cannot be. Now, if you look at all the IV curves, this is now the IV curve of 1,000 spots, and you can see it's all over the place. So how can it be that we have open circuit voltages that are higher and clearly lower? Now let's take a look at that if we do a histogram of all these spots. And this is now on the right-hand side a histogram where we show the distribution of all measured voltages. And you can see it can be easily fitted by a Gaussian curve. And that the peak of this is at 0.748 volts plus minus 0.2 volts. So it's quite a narrow distribution. And what we find experimentally, if we put a connecting contact on the solar cell that then collects on a large area, let's say 2 or 4 square centimeters, it comes out 0.74 volts. So it seems that the local voltage, the average local voltage, is identical to the voltage that we measure by summing up of all the various IV curves, but you can have hotspots where the open circuit voltage is much higher than what you would expect. And that means that we have local potentials, and we found out also where these come from, but I don't want to talk about that because that's another talk then for itself. But the question is now, what are these hotspots? What types of states are there? Are there really band-tail states? And that we can only do by measuring this with a different technique. You can also measure and integrate the current over basically the brownish area, that homogeneous area. And if you do that in the IV curve, what you find if you average of all those areas, it's this blue curve. And you can see the blue curve is a negative current. So again, as I said, all the homogeneous area is a photocurrent. So we have separated dark current from photocurrent. And to my knowledge, the first time that this has ever been shown in a solar cell. Now, if you do a calculation, we use computer simulations to calculate IV curves. It's a 3-dimensional device simulator, very sophisticated. And this is the IV curve that we expect. You can see what comes out is this open circuit voltage here of 0.75. And you can see the red curve here. That is the actual photocurrent that has been calculated. And if you compare to that blue curve, you can see it kinks around 0.7 volts. This is exactly right here where it kinks. So it seems to fit on what we simulate. So somehow that is extremely important for how that solar cell is working. Okay, so the bottom line is the homogeneous area is only photocurrent. We call that the primary current, and the hotspots, the current patches, that is the dark current. And we want to know what produces that leakage current in the solar cell. So what is the microscopic origin? Now, as I said, all these local states that we have at that interface, they at some point will be occupied by an electron or by a hole, and by that they can carry a spin. So if we now look at the magnetic properties of these features, then maybe we learn what this actually is. And that means we now are switching gears and we go to magnetic moments. Now, if we have these features in there, these states that are occupied with an electron, and we are doing this without an external magnetic field, then these local magnetic moments, they can orient in any direction. And since we have 10 to the 10 per square centimeter and even more in that sample, it means we have all kinds of orientations. And if we sum up all those local individual magnetic moments of the radicals, of the spins, the sum of that is going to be 0. They add up to a null magnetic moment. If we now apply, and that means the occupation of spin up or spin down is equally distributed. They have the same occupation. Now, if we apply an external magnetic field, then the energy levels are lifted with respect to the magnetic quantum number, ms. Depending whether it's ms minus 1/2 or plus 1/2 spin up or spin down, we get different energies. And that is the so-called Zeeman splitting that you might have heard of. It's called Zeeman splitting with one E. Okay, so let's look what that Zeeman splitting is actually doing. By applying this, we are splitting the energy levels linearly with the magnetic field. We get a 2-level system if it is spin 1/2. And now, due to the Boltzmann distribution, we will have more spins being in the parallel than in the antiparallel state. And that means we now get an uneven number of spins in the upper and in the lower level. And if you now sum up all those individual magnetic moments, you will see that we have more that are parallel, so they point in that upper direction, like this one here, this one, and that one, than those pointing in the other direction. And you can now calculate very easily how large the difference between those two occupations is if you assume that everything is done by Boltzmann. And that is the case once you are above 1 Kelvin, you can basically use Boltzmann. And if you do that, what we find is that the occupation difference between those two magnetic moments can be calculated through a Taylor series of this. So we calculate the difference between spin parallel and spin antiparallel with the respect of the magnetic field. And we find it is basically the number of magnetic moments, NS, we have in the system. And then there is a factor that is proportional to the magnetic field and anti-proportional to the temperature. Don't mind the details. And if you calculate that now for a magnetic field at room temperature of 0.35 Tesla, that's a typical field we use, we can see that only 0.08% of all the spins contribute to that total magnetic moment. So we are seeing a sub ensemble of all those magnetic moments, but nevertheless, they contain all the information that is necessary. So that polarization is extremely small, okay? If you go to a lower temperature, so in case of going from room temperature, here you go to 4K. In that case, of course, that thing is boosted. And then the polarization effect is 5.8%. So it dramatically increases at lower temperature. If you now also increase the magnetic field, let's say from 0.35 to 10 Tesla at low, then you can see that almost 100% are polarized. That means all the spins will contribute. So you would like to do that experiment at high magnetic field and at low temperature, but this is not where a solar cell is working. Solar cell works at room temperature, so we have to do the experiment at room temperature, and the sensitivity is not enough to do that with such a magnetization technique. And I will show you a trick on how you still can measure, although this sensitivity is not there. Okay, now let's look at how you do that measurement. If you have enough magnetization, you put the sample into a magnetic field, and this is the magnetic field of a large electromagnet that we have in the lab. We get the Z-man splitting. You can see this is the Z-man splitting right here. This is the magnetic field that is increased, and this is the energy. You see that nice Z-man level splitting. And what we now do is we do two-level spectroscopy. We apply now a electromagnetic radiation that is shown onto the solar cell or onto the solar cell material. And if the energy of that incoming radiation at a certain magnetic field is in resonance with that splitting, we can induce a so-called magnetic dipole transition. So the magnetic moments couple to the magnetic field of the photon field. And if you calculate this, assuming that this is a free electron and that has G equals to 2.0023, then you find that at the typical 0.35 Tesla, what you can do with such an electromagnet, we get an energy splitting of 41 micro electron volts. So it's minute energies. Now, the problem with this is it's very difficult to measure because we have this very little polarization. So that means we need tricks to be more sensitive, and that is a resonator. We put the whole sample into what we call a resonator, and 0.41 micro electron volt convert into a frequency of 9 gigahertz, and that's microwaves. So this is centimeter waves, and that means that cavity has centimeter size, and the sample is in there. And inside that cavity, if you look at that cavity, you will find that the magnetic field distribution is such as that we get a hot spot in the middle. The electric field is maximum here and there. So it's the magnetic field that is separated from the electric field that now drives the spins. Due to the fact that we need a cavity for the sensitivity, it means we cannot change the frequency. We can only change the magnetic field, and that's why in magnetic resonance, you, in most cases, change the magnetic field and you use monochromatic light. So if we do that, we get a very nice absorption line if we have spins in our system. And this shows here sort of a simplified picture of amorphous silicon. For instance, here we have a defect state right here that has a p-type orbital. And if we measure that, we get this curve. And since the intensity of any dipole transition is related to the difference in occupation, the area under this curve is basically proportional to the number of defects or number of spins we have in the system. So with such a transition, we can quantitatively measure how many defects are there. Now, how do we get now this probe character of measuring this? Now, I change colors. I go to the blue color to now look for nuclear spins. For instance, here we have a proton. This is a hydrogen atom. That hydrogen atom also has a spin, namely hydrogen has a nuclear spin of 1/2. That nuclear spin can be up or that nuclear spin can be down with respect to the external magnetic field. And that means this one is inducing a local magnetic field at the position of that dangling bond. If the proton would not be there, we would get this transition here. But now the proton is there, and let's assume this is there for all of the states. It means we have to take that into consideration, and that means that our energy level splitting now looks different because each level is now split into two levels, here and there, spin up and spin down of the nuclear spin, and the same down here. We get a splitting. And we now again do the transition. The transition does not change the nuclear spin, it only changes the electron spin. And then we get two lines that are centered around that previous line. And the area under this curve is the same as before. However, we now see two lines. And that splitting is exactly now the dipole coupling that spin is inducing. And so with this, you can now measure distances. You can measure local wave functions interacting with that proton, and you get very precise information about your local network. And that is the strength of this type of resonance, that you magnetically map your environment. Okay, as I said, unfortunately, it is very difficult to measure a single spin. We're currently almost there to do it with a single spin, but not yet. But in the typical experiment that we do, the voice, let's say, of one SPI that we have in the sample is by far not enough. So we need about 10 to the 10 to 10 to the 12 of these species that talk to us and that we can read out the information. So it is quite a lot, so we cannot work with too small sample volumes. And it is so that chorus of the 10 to the 10 to 10 to the 12 defects that then give us all the information that we need. And now, of course, the local environment, the local disorder, will now change those local absorption features that we have of each individual spin in the system. And that is what makes up then the total signal that we measure. Without going into the details, I will now try to explain that in a bit more detail. So as I said, I'm recapitulating. We have a probe. For instance, we can use this dangling bond right here as a probe. It's a broken bond, that radical. And then probe, for instance, the protons here. We probe silicon-29 because in the material, silicon has 4% of silicon is silicon-29 that also has a nuclear spin. So we can use the nuclear spin of the silicon, we can use the dangling bond, and we can use the proton as probes that interact and tell us something about how that network is being set up. And there's other probes. We have bonds that are strained. This one, for instance, can be very strained, that bond. And then an electron can be trapped right here. And this produces a tail state. So it can only trap an electron right here. And that is also a probe that we have. So there's many ways on how we can measure this. And I will use some of these probes to show you at the end what that leakage of the solar cell is. Okay, so remember, magnetic probes sense the local structure of that network. Okay, now let's see how we can draw more information from this local magnetic moment. And for that, we have to look into the spin resonance. And without going through tons of formula, what I've done is I've basically plugged in the formula into a graphics program and then showing you graphically what is happening, because then you directly see how things are going on. Now let's assume we have our sample. We have our radicals that we're interested in, strained bonds or dangling bonds or whatever. And they all form together that occupation difference, that magnetic moment that we can measure macroscopically. If you put that into a magnetic field, the magnetic field has a strength B0. Let's assume this is 0.35 Tesla. Then that magnetic moment will possess around that magnetic field. And this is what I'm showing in this animation. I show the x-axis here, y-axis, and the magnetic field is along the z-axis. Now, what is that precession frequency? Well, you can directly calculate that. It is the gyromagnetic ratio of that magnetic moment times the magnetic field. That gives you the so-called Larmor frequency. And the gyromagnetic ratio is determined by the G factor that is in silicon, basically the spin-orbit coupling of that species. And this is about 2.8 megahertz per Gauss of magnetic field. And that means if we have 1 Tesla of magnetic field, we will have here 28 gigahertz of Larmor precession frequency. So that magnetization is spinning in real space with 28 gigahertz in real space. Now, the question, of course, comes, and that is one of the questions that I have put into the question, how do you call that thing? The question maker or the question answerer? So,
Mentimeter.
Yes, exactly. And now my question is, we have that rotating magnetization. And as I said, when we induce a magnetic dipole transition, we're going from a spin up to a spin down state or vice versa. Now, how the heck is this possible here? So the question is, how can we invert that magnetization from the plus direction? So all those spins show up into the plus direction. Now into the direction down here. So we want the magnetization to process down here. How do we do that? And the possibilities are, yes, you can open up the question. You throw me out,
yes.
and then
I have put the question into the Mentimeter. I've put a link to the chat, so I hope that everyone can access the chat. And just you should be able to just click on the link, and the first question should be already there.
Okay, and so the possible answers are 4 answers I'm giving. So one is I'm applying a constant second magnetic field that is perpendicular to the first magnetic field. So saying I apply a magnetic field in this direction, a constant magnetic field. Second answer is I'm simply inverting the external magnetic field very quickly to the minus direction and then again into the other direction. Or I have an oscillating magnetic field in the XY plane. So this thing here is moving in the XY plane, and the frequency clearly has to be lower or higher than that Larmor frequency. And the fourth choice is that oscillating magnetic field in the XY direction directly has to hit the Larmor frequency.
Yes.
So those are the 4.
Everyone who clicked on the link can actually see the options.
Mm-hmm.
And so I'm getting now the first results. I don't know how much time should I give them?
I don't know.
One more minute, Klaus. What do you think?
Yeah.
An easy question?
Yeah. Since you don't get money for the correct answer, and I will not kick your butts if you give them the wrong answer, you just click what you think is correct.
Okay, so I am pleased to say that almost everyone is like, no, not almost everyone, but the better half is clicking on the right answer because I already know the right answer.
You're clever. You're clever. You're very, very clever. It took me 10 years to learn what the right answer is. Honestly,
I only had to look into your email.
Okay, so but we can now discuss this.
Yes.
So if you do that, if you apply an external magnetic field that is fixed in space, let's say this is a B1 field, then the external magnetic field and that B1 field will add together to a total magnetic field pointing in that direction, and then the spins would simply oscillate around that. So it would not change that going into the different spin states. So that will not work. What will also not work is by quickly inverting magnetic fields, because it simply is not possible to do it in that speed as you have to do it. It is an oscillating magnetic field. And I will now show you what that oscillating magnetic field is doing. If that magnetic field is oscillating in the XY plane, and this magnetic field is not at the Larmor frequency, it's below or above, only when they align for a very short period, it can induce a torque on that magnetic moment, that is the red line that is running. So you can slightly do something, but you're way off resonance. However, if you directly hit the Larmor frequency with that oscillating magnetic field, then the torque that is induced can pull down the magnetization. And this is the true, I've solved the equations, and this is what the magnetization would do in real space if you now apply that magnetic field oscillating at the same frequency as the Larmor frequency of that spin. So that is, of course, magnetic resonance. You have to hit that Larmor frequency. So you're sensitive to that Larmor frequency. Now let's do a trick. Because it becomes much simpler, let's start to rotate that coordinate system with the Larmor frequency. So instead of having a fixed coordinate system, we are rotating, and we are rotating this with the Larmor frequency. That means this whole thing is now rotating with the Larmor frequency right here. And then we give the axis the name X prime and Y prime. So this is now rotating. And in that rotating frame, it means that the magnetic field is now fixed, because we're rotating as quickly as that B1 field is moving. And that means we basically have a fixed magnetic field in this frame. But we already know what a fixed magnetic field is doing. A fixed magnetic field is basically inducing a Larmor precession around that magnetic field. Where's the external magnetic field? The external magnetic field is gone because I'm rotating the coordinate system. And that means if I'm the observer, everything stands still. And it means for me, as somebody rotating with the Larmor frequency, the magnetization stands still in space. If I now switch on this magnetic field right here, it's going to stand still, but now that magnetization is starting to again precess around the magnetic field axis, however, much slower, because now it is being driven around the X prime axis. And this rotation frequency, that is called the Rabi frequency. And it is basically gamma times the strength of that microwave field. So we're now inducing transitions between spin up and spin down, like this. And if you would, for instance, in that experiment, stop the Larmor frequency at some point, let me see whether I can do that here. No, I cannot. Somehow I have the problem with the animation again. Let's assume I stop while that magnetization is pointing to the Y prime direction. So then I switch off that magnetic field. Then that magnetization will remain in the X prime, Y prime direction. So it's basically then on that axis. And what does that mean? It means the Z direction of the magnetization is 0. But what does that mean in terms of a simple two-level system that we have down here? It means that we have equal occupation of the spin up and the spin down state. So if I can stop that magnetization exactly after 90 degrees, so I'm keeping the B1 field on for 90 degrees, then we have equal distribution of the two-level spin system. And that then is called spin saturation. We have same occupation of both states. And that is a very important thing because that's called a pi/2 pulse if you do that. And if you keep on flipping, you see the Rabi oscillations up, down, the spin is rotating in that frame. And that is actually magnetic resonance. Okay, now how do you measure? And so now we have here a little demo experiment. I have, because I could not bring it, of course, I had a student film it in the lab. And this is an experiment where we have a Helmholtz coil. I hope that you can see that. Well, my laptop is frozen. I have to wait. Something is happening here. Yeah, those Helmholtz coils, we have a little coil.
Mm-hmm.
Well, I cannot draw anymore. My mouse has disappeared. Coil is generating the B1 field. That is where the B1 field is, right here. And this is the Helmholtz field, the B0 field. And now you can stick a sample in. This is the sample right here. This part is the sample right here. And this is how the experiment looks like in the lab. This is the Helmholtz coil. This is where we stick the sample in. And let's look what happens if you now measure this and you sweep now the radio frequency that is driving the spins. And that's what we've done in the lab. You see now the student is putting the sample in, and you can see now this dip here, that is the absorption of the spins. You've taken it out and the absorption line disappears. So we have indeed done absorption with that with this very simple experiment. Now what you can do is you do the same experiment, but now you mimic a local change in your network, and that you can do by using a little magnet. So the student is holding a small magnet, and now look at that resonance curve. The closer you come, that line is shifting because that local magnetic field is superimposing with the external magnetic field, and that is shifting the line. So we're very sensitive to those local magnetic fields, and that's what you would do in real life too in the lab. The next thing that you can do in the lab is basically cooling the sample. As I said, when you cool, Boltzmann is in favor of you. You get a better difference between the spin up and the spin down. If we do that in the lab, see it's now nitrogen, you put it in, and you will see that the resonance now is much deeper. You see that this dip is about a factor of 3 deeper than before. And now it's slowly recovering because the temperature is rising and going back to room temperature. Okay, so that's the effect of temperature. That is the Boltzmann effect that you see. Now comes another question. Let's do the next experiment. Now let's take this this little coil and turn it by 90 degrees. So again, we're in exactly the same magnetic field. It is exactly at the same position as before, but now we have rotated this by 90 degrees. Before it was in this direction, now it is in that direction. And now comes again a question. How is this going to affect my my absorption measurement of the EPR? Is the EPR signal going to be exactly the same because the sample is exactly the same position or almost exactly at the same position? Is the signal shifted to the left or to the right, so in frequency, depending on the rotation direction, whether I moved it from the left to the right or from the right to the left? Does the EPR signal just vanish? It's gone. Or does the EPR signal broaden? So 4 possible answers. And
the voting is open again in the Mentimeter on the link in the chat. The next question should be already visible.
Okay, and then just tell me if you think that enough people have thought about it and clicked to the answer.
Yes, it's
okay.
Pretty much the same result.
Okay, good.
Previous questions, majority of the people are voting on the correct answer.
Okay, so let's do the experiment. You can see now exactly.
Your lecture is very, very clear to follow. That's good news.
So now the student is putting in now the sample into, again, that coil where we drive the B1 field. And you can now look at this. Nothing is happening. Why is that? Why can't we see a resonance? Well, because the driving B1 field in that animation that I showed has to be perpendicular to that external magnetic field. And now it is parallel. In parallel mode, we cannot get a torque on the magnetization. So that is essential that they are perpendicular, at least that there is a certain angle in between the two. So great students that you found this out. Okay, now comes maybe the most difficult part, and I will only highlight what this is, and that is now if you induce such a transition and you stop that B1 field at a certain position, how does the system relax back to its thermal equilibrium? If you, for instance, have that two-level system, you're exciting the spins, let's say, into equal population. This spin is going back into its ground state, thereby emitting the energy. So it's emitting a microwave photon. But what is the driving force? What is it driving? This is a process that can only happen if there is a local magnetic field that hits exactly that resonance. So we need some local magnetic field, and that local magnetic field has to be in the XY prime direction. So it has to be perpendicular, and it must have the right frequency. So if we have phonons, this whole lattice is shaking, then maybe some modulation of the spin-orbit coupling will induce in the right order, the right frequency, and then there's a certain probability that that spin will relax. And this is called an energy loss, an energy relaxation. That's called a T1 process. So that's a very important process. It's related with damping of the magnetization in the Z direction. It's an exponential decay. The second effect that we have is so-called phase coherence loss. If we have all the spins and all those spins are rotating with the same frequency, let's assume for a very short period of time, that spin is seeing for a split of a second, a very local different magnetic field. It's going to rotate a bit faster, and it means they get out of tune, they get out of sync. And if that happens over and over again, all those spins that should be all synchronized, they get out of tune. And that is called a phase loss. And this can be understood easily by assuming that that energy level here is fluctuating by a certain local magnetic field. And that local fluctuation modulates the Zeeman splitting, but it does not induce a flip. It only induces a phase change. And that phase change then leads to a relaxation process, but only in the XY prime direction. And that is called a T2 process. And that T2 process basically tells everything about the spin lifetime. It's the T2, not the occupation, that where all the physics is connected to, and that is the stuff that you measure with magnetic resonance imaging, MRI, in if you're, for instance, in a hospital. But then it's the nuclear spins. So what that does is then, in a very simple picture, we are basically applying a microwave field. We're flipping all the magnetization in the XY prime direction. And now, because local fluctuations of the magnetic field happen, some of the spins for a short period of time get behind or are a bit faster. So the total magnetization, that maybe here is 10 to the 10 spins, start to spread up and then distribute over that whole XY prime axis. And at some point, all the magnetization in the XY prime direction is gone. And that means there's no more coherence of the spin states. And that is, if you now measure that magnetization in the XY prime direction, that leads to a exponential decrease with exactly that relaxation time, T2. And that is the most important time that we have in magnetic resonance. And that is what you want to determine, because that gives you all the local information about that system. And the way we measure it is in the rotating coordinate system. We have in principle two coils. They rotate in the cavity in principle. It is a coil in the X prime direction, one in the Y prime direction. You induce now with your microwave that the magnetization flips into the X prime direction. Once it is right here, this detector will see, oh, a magnetization is inducing a voltage. So that means in the MY direction, I will see a signal. And if this now becomes smaller and smaller and smaller, that signal will disappear. So this detector here will see this decay of the magnetization. That detector here will see nothing because there is no magnetization in the X prime direction. So that is basically 0. And this decay, this one here, we call the free induction decay. And if you Fourier transform that free induction decay, you can fit it, of course, with an exponential. So in this case, it's 90 nanoseconds. That then gives you the complete spectral information of the system. So if you Fourier transform now the MXY and MY component, then you transform that into frequency domain, and the red curve is the absorption, and the blue curve gives you the dispersion signal. And that you maybe know from optics. That is then Kramer-Kronig relation that connects those two entities. So in principle, it is a optical spectroscopy, and the width of this line, that width that we have here, that is the T2. So the width of that line tells you what the T2 time is, and that is the beauty of magnetic resonance. Okay, now and it's a Lorentzian, of course.
Klaus, sorry
yes?
to disturb you again. We are really pushing the time now.
Okay,
so
then it means I'm jumping then a bit now forward. Sorry about all those technical issues. So you can then set up the spin Hamiltonian. I will not do that, but it will tell you how the different interactions are leading to different effects. They are sometimes magnetic field dependent, sometimes they're not magnetic field dependent. That you study by measuring at different magnetic fields, and that gives you then the overall picture of the spin Hamiltonian of your local system. And that is what magnetic resonance is about, setting up that local spin Hamiltonian and then doing a simulation to see whether your spin system is working correctly. Okay, now, yeah, we can skip this. This is not so important. This is how resonances change. I can skip that. It's just spectroscopy. But I now come to the final slides. Yes. And that is the disorder that we have in the system. If you have all the spins looked alike like this, then all the spins, if they all have the same environment, that defect here, then adding 1, 2, 3, 4, etc. numbers of spins will just simply increase the intensity of the absorption that you measure, and the width is going to be T2. Okay, that's the width in frequency units. However, if you have now disorder, let's say one bond is basically a bit strained here, or one bond is a bit longer, or there is a proton sitting next by, that local wave function is going to change, and that is going to shift the resonance in frequency or magnetic field space. And then you get now a inhomogeneously broadened line that is much broader than the original line that was only T2. So basically, we now get a broadened line, and all the nice features that we had before, they disappear under the disorder. And the only way that we can get rid of this disorder effect is through echo spectroscopy. And that is the second last thing that I'm going to show you. How can you again reveal the original line shape in an experiment? And that is basically the runner's analogy. Imagine that we have runners in a stadium, and those are all my individual spin packages that I have in the magnetic field. If they all do the same, they all have the same frequency, they will run in the stadium. Hang on, something went wrong. They will run in the stadium, and they will all run at the same angular speed. So they will all be synchronized. We do not lose a single runner. That means the coherence time is going to be very, very long. So they can run around hundreds of times, and we will maintain that coherence. If we measure at some point, then this is basically a measure of how they keep together. Now let's come to the fact that we now have local magnetic fields. Some spin sees a magnetic field, the other does not. It means they run at different paces in the stadium. And if they do that, and I have animated that again, it means they are now running at different angular speeds, and it means at some point we have complete disorder with respect to the runners. So they start to distribute in the stadium. The question is now everything lost? No, it is not, because if I tell the guy in the stadium to say, guy, when you shoot your gun, all run back, but maintain your angular speed, they will all come back at the beginning position and they will form an echo. So although every runner is individually different, I can force them to become coherent again if I reverse their order of direction. Now, what is a T2 process? In a T2 process, it means locally a runner is running a bit quicker or is running a bit slower. So let's do that again in this animation. The runners are running. And now, for instance, this runner is interacting. It stays behind a bit. And now it's getting desynchronized. I tell them again, go back. They all run back. Again, another runner is hitting another runner. For instance, here, they get a bit more desynchronized. That one gets behind. And now, not all of the runners are appearing at the starting line. So my echo intensity is smaller. And you can see by changing this timing, you can measure how that echo disappears, what those relaxation times are. And what is a T1 process? Well, in a T1 process, one of the runners basically, that's the T1 process. All of the runners are running, but now one of the runners is basically just falling. He gets a heart attack, and he can no longer run. And now all the runners are running back, and maybe another runner is getting a heart attack. You see, I love running. And again, we get a reduced echo at the end. And in magnetic resonance, you can use that now to measure that echo intensity as a function of time. And that's the so-called Hahn echo. Basically, by using different pulses, you can now convert the echo and measure by changing the pulse lengths between those pulses. You can now measure the true T2 of your system, although you have disorder. Okay, now how do we use that in our experiment? That is the last thing I'm going to show you. We have calculated now at that interface the magnetic properties of those states very close to the conduction band and to the valence band and to the defects. We know how the wave functions look like. We have calculated those, and we can tell what the G tensor of that specific defect is, of a conduction band tail state, of a dangling bond at the interface, or a hole state that is close to the valence band. And they have very, very different magnetic features, and those we can then use to fit our measurements. And that we have done in our experiment. We have now basically used our solar cell. We have made such a solar cell with a leaky contact, and we have calculated now what the tunneling transition is from that leaky contact to the surface. So we used DFT to calculate basically that tunneling probability. This is what we have measured. This is now measured at low K, so that we at low temperatures, so that we have a better resolution. This is what we calculate how such a state looks like. And this is now the image if such a state is occupied by one hole, by two holes, or if we have three holes, meaning that we have two states next to each other. And if you now compare to that image, and this has not been published yet, we're on the edge of doing that, you can see these features appear exactly in the way that we calculated. So sometimes we have three holes together, sometimes we have one hole together. This is paramagnetic, and this is paramagnetic. We can calculate now the G-tensor of these states, and now we only have to measure that tunneling current out of the solar cell. And that is the last result I'm going to show. We've made very small solar cells. We connect the solar cells electrically, and then we do a magnetic resonance while we drive charges through that interface. And while you do that, these charges hop through those states. And imagine you're hopping from here to there, and one spin is sitting here, and the other spin wants to hop to that already occupied site. If those spins are parallel, they cannot hop. It's Pauli principle that forbids. However, if I turn that spin, it becomes allowed. So by measuring that current while I'm doing that Rabi oscillation, I should see an oscillation of that current if that is really the effect. And we have done that experiment, and indeed what comes out is we see a very nice Rabi oscillation of the current in the solar cell. This is the Rabi oscillation that we have measured. The sensitivity is 100 electrons, 100 states that we measure, and then we fit the resonance with the G-tensor that has been calculated, and look what a great match we get for, this is amorphous silicon, for different frequencies that we use. And this shows that it is indeed that tunneling step that we have identified through a local spin probe, through that Pauli blockade, that this is the mechanism that produces the leakage in the solar cell. Okay, so summarizing, we find that leakage through that contact, through that tunneling transition, has been identified both by conduction AFM, by spin resonance measurement, and by DFT calculations. And that then leads to a, I would say, almost complete picture of the understanding how that selective contact works. And how can you improve that contact? Well, you have to reduce the disorder at that interface to get rid of those localized states. And that's basically what we're currently trying to do to get to that maximum efficiency of almost 30% with these types of solar cells. Okay, summary means it took me 30 years to understand this. Believe me, I worked 30 years on this, on and off, but now I think I have a good understanding of how this very complex interface works. And we now have identified ways on calculating this and really measuring this on a very local nanoscopic scale. Sorry for all the technical difficulties that we had. I'm sorry that I was in between you and the dinner, and I thank you very much for your attention.
Thank you, Klaus. And some technical difficulties were also on our side. And now we can see all the hubs are clapping, of course. So let's quickly ask some questions. I mean, it's really shame that we don't have much more time to ask the questions, but that's just how it goes.
Well, that's how it goes. That's how it goes.
Yeah, exactly. So if there are any questions, please, you can either ask in the chat or maybe just notify me that you have the questions, and we can do it via audio. And just to give you time, I'll kick the questions off. From my point of view, it was really interesting because I deal with AFM. So of course I have a lot of AFM related questions, but maybe start with something a little bit more general. So my first question is, you said that the selective contacts are 8 nanometers thick. Yes. Or thin. Is there some kind of a theoretical limit on how thin or thick you can make them, or
yeah,
how thin they can be?
Yeah. So the reason why they have to be 8 nanometers thick is that if you deposit 8 nanometers, it means it's done in a reactor. You will get inhomogeneities in the thickness over the whole solar cell. I mean, this hole has to work over 6 inches on a wafer. And if you get local disturbances, you will get basically a hole in your contact. And a hole is a leakage. And that means you get a shunt basically at that point, and that means it is no longer a selective contact. So the main issue is it has to be thick enough that the probability of getting such a shunt where the amorphous silicon is not completely closed is reduced. And that is one of the effects. There's other effects that also come into play, but this is the main effect, I would say. Second effect is it is not as simple as I said. It's not one amorphous silicon that we put on top of that solar cell, but it's a graded amorphous silicon. So we start with an intrinsic material, no doping, and then we slightly increase the doping to get a better selectivity. As I said, the doping increases the conductivity, and a selective contact has to be as conductive as possible for that one charge. For the electrons, it has to be electron conductive. For the holes, it has to be hole conductive. So you dope with phosphorus or with boron. And that also takes time until you get that boron and that phosphorus in there. So you need a certain thickness to get that conductivity established. And the thicker you make it, the better the conductivity will be, the more selective the contact will be. But the thicker you make it, the less light goes through. So you're basically at one point blocking again the contact. So it is quite a complex interplay of getting everything together to get that maximum efficiency in your solar cell.
Okay, thank you for the answer. We have one from Martin Miller. He wants to thank you for the lecture, and he's asking about that he showed the local IV curves on solar cell measured in AFM with a quite broad distribution of VOC. Those IV curves with VOC larger than the average ones were related to those hotspots around the combination centers, right?
Yes.
And what is the source of those low VOC curves?
Okay, what happens is the following. I spoke mainly about those, let's say, states that are induced by the disorder, but we also have defect states at that interface. We have analyzed them, we know how they look like, but they currently don't play a major role. However, if you have a local defect sitting next to that band-tail state where you tunnel through, imagine a charge is being trapped right next to that center. That local charge will induce a Coulomb interaction and lift local the potential up or down, depending whether it's a positive charge or a negative charge. So a negative charge is reducing the potential, a positive charge is enhancing the potential. So you can tell basically from that, if a local charge comes, the leakage is going to be reduced or it's going to be enhanced. So it's a local charge that you see. That, however, means if you measure that current and you wait long enough, you can see the charge going out, the current is going to change, and that is what we see. We see random telegraph noise. So if you measure as a function of time, let's say 100 seconds on that spot, you can see current jumps up, current jumps down. So, and that, from that random telegraph noise, we could measure basically the energy depth, and we found out it's about 0.6 electron, 0.7 electron volts, and that's the state of a defect. So it is a defect that is inducing this effect. We're pretty certain about this.
Okay. Thank you very much.
Mm-hmm.
Seems like everyone is really hungry. So I don't really see many questions coming in. I have one additional one regarding the AFM.
Yes.
So you show the AFM pictures with a very nice resolution, like a few nanometers only.
Yes.
And you mentioned it's in UHV, so I presume that this is like the nature of the AFM in UHV.
Yes.
But did you find any effect of the tip nature, of the tip material, of the tip bluntness, or so on, or is the electrical contact stably very small?
So yes, the tip has an influence. Of course, tip artifacts, I mean, you're well aware of this, of course. You directly see the tip artifacts. You get basically two tunneling features from your tip. We have checked this for very different materials, and we found that platinum works the best as the tip that we use for silicon. It makes a good almost ohmic is the wrong word, but it makes a good contact with the amorphous silicon. We have first simulated the contact material through the tunneling in our simulation to find a good material, and then it turned out platinum is the best for this. So that is one. Second artifact that we get is, of course, due to the height. So depending on how high the tip is over the sample, when we measure at VOC, no current is flowing at VOC, so this should be completely independent of the tip height. But since we have local charges being trapped, we see the local potential, and from that we can then calculate how much these local potentials distribute. It's in that paper that I have cited.
Yeah.
So yes, there are artifacts. We see those artifacts. We also see some, if you do a good analysis on all the features that you have in the background, we can see some other artifacts, but they're not related to the message that we bring across, namely these hotspots, these local, tunneling sites that we have in the sample. Yeah.
Okay.
But you have to really clean the sample first. It is, you need a student that is, and this was a student from Ethiopia. And this is a guy, if he goes to university, he first had to walk 1 week to get to the bus station. And you need a patient guy like that to clean that sample surface over and over again until you have a stable situation to get sub-nanometer resolution. So we have 0.6 nanometers, so 6 angstrom was the resolution of our experiment on amorphous silicon. So it is really quite an amazing resolution that we achieved at low temperature.
That really is incredible.
Yeah.